So this next example is another kind of famous one where we're going to have a roller coaster on this track that we see below. It's got an initial speed and we're looking to find, well, what's its maximum speed? And again, the track is frictionless. That'll simplify our calculations. But without further ado, let's get started on this question. So at the beginning, I want to give everyone a hint, and that is to tell you the important dimensions of this track. So the first one that's going to be really crucial to us is this 9.5 meters. And the second one is this 0.5 meters. Now, what's interesting about these points and what makes them the important ones is that this one here, the 9.5 meters, that's our starting point. And this 0.5 meters, that's our lowest point that the track reaches. So in other words, that's going to be the point which we have the least potential energy. So least potential energy. And since energy cannot be created or destroyed, if it has less potential energy at that point, that means it has to have more of a different kind of energy. And what energy is it going to have? Well, on this track, the potential energy is going to get converted to kinetic energy. So therefore, it'll have the most kinetic energy at this point D. That is because, again, it is the lowest point. So what is the maximum speed? We know it's at point D. It's at point D. Again, just because it's the lowest point, the least potential energy, and therefore that potential energy has to be turned into something. It's turned into kinetic energy. So let's write out our energy balance equation. So energy total initial is equal to the energy total final. This is just a straightforward saying energy cannot be created and it cannot be destroyed. Any energy in the system that's at the beginning will have to remain there in the end. So let's look at the initial energy. What kind of energy do we have at the beginning of this question? Well, let's look. We have some kinetic energy because we have a speed, and we have a potential energy because we have some height. So let's write those out. Our EG, that's our potential energy initial, plus EK initial. And that is equal to, what energy do we have at our final point? So that is going to be at this point here that we're measuring. What kind of energy will we have there? Well, it's going to be the same thing. We're going to have some kind of kinetic energy, so our roller coaster will still be moving forward. And we also will have some potential energy because we're still this 0.5 meters above the ground. So there will be some potential energy, not as much, but there will be some. So let's write that out. Potential energy final plus kinetic energy final. So let's take this down one step further and write out these values. So potential energy initial, that's going to be our mass, our initial mass. Just going to write a M. G is for our gravitational constant. And H initial, so that's our initial height in green. Plus 1/2 M, and I want to keep these color coded, our initial velocity squared. And if you want to see where this initial velocity comes in, it's going to be this purple value. It's 15 meters per second. Is equal to EGF, so our final potential energy, that is our MGH final, that's going to be this number here plus EK final, which will be 1/2 mv final squared. And this v final squared, this is our unknown. That's our unknown. All right, so we got a good equation started here. Now let's start plugging in values for each of these variables. You'll notice we have a lot of m's. That's the mass of the roller coaster. And in the question, we're never given a mass. And at first glance, this might be an issue because, well, we need a mass for every single one of these terms to calculate our energy. But in reality, we don't need a mass. And I'll show you that in the next step after this. But for now, I'm going to keep them as n's. You'll just see that later on they're going to cancel out, and it's pretty interesting how that works. But in the meantime, I'm just going to write this equation with the values plugged in that we know, and our m's I'll just keep as an m. Our g is 9.81 meters per second squared. And our h is 9.5 meters, remember, 9.5 meters. And then the next term is going to be 1/2 times m. And in the brackets, our value for the initial velocity, remember, is 15 meters per second. It'll be squared. So that 15 meters per second, remember, came from up here. And all that is equal to m times 9.81 meters per second squared times h final, 0.5 meters. I'll show you that again. That comes from here, this point D. Our height is 0.5 meters. Plus 1/2 m v final squared. Okay, so we're making good progress now. We just have to continue bring this equation down one more step by multiplying some of our terms. So in each term we can multiply some values. I'll do the 15 squared here, and I'll be multiplying these values. So here's what we get. The next step, m times 93.2 meters squared per second squared plus m times 112.5 meters squared per second squared. That is equal to m times 4.905 meters squared per second squared plus 1/2 m vf squared. And this is the point where I'm going to divide out this mass. So you'll notice that we've got mass, 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 and mass. If we divide everything by m, so divide both sides of this equation, whatever we do to one side of the equation, we can do to the other. So if we divide both sides by m, we can get rid of the mass term. So that's what we're going to do. And our equation is going to become 93.2 meters squared per second squared plus 112.5 meters squared per second squared is equal to 4.905 meters squared per second squared plus 1/2 mv squared. There's our VF. Remember, this is our unknown term here. So now let's, sorry, this m is gone now. Remember that m was taken away when we divided both sides by m. So now let's work on isolating this value here. Our unknown, let's work on isolating it. So this term's obviously going to have to come to the other side as a subtraction. And for now, I'm just going to drop these units because they're the same on every term. We'll just remember to pick them up later. It's 93.2 plus 112.5 minus 4.905 is equal to 1/2 VF squared. And these three terms will get a value of 200.9 or 200.795 meters squared per second squared is equal to 1/2 VF squared. So bringing this 2 up to the other side, here it's a division, so on this side it's going to be a multiplication. 2 times 200.795 is equal to VF squared. The value for that is going to be 401.59 meters squared per second squared is the units, is equal to VF squared. And now that we're running out of room, I'm just going to bring this up to the top again. So I'll just rewrite what we have there. So 401.95 meters squared per second squared is equal to VF squared. Same thing. I'm just going to pick up higher up on the page so we have some room to finish this. So we've almost got this isolated. There's just this squared term that we have to get rid of. So we're going to do that by square rooting both sides. And the square root of this value here will be 20.04, and the units meters per second is equal to VF. So at point D, our speed is 20.04 meters per second. And that is our Vmax. Vmax is equal to 20 meters per second. And I'm just keeping two significant digits because in our problem, that is the number of significant digits that we're given. So in our final answer, we'll keep that consistent. So our Vmax is 20 meters per second. And I'm just going to write a statement to conclude this. Therefore, the max velocity which occurs at point D will be 20 meters per second. And that is the solution to this problem.